Hey, welcome back to your favorite calculus class. We're going to take a look at derivative as a rate of change. So if you remember, the old f prime of x is limit h goes to 0 of our difference quotient. All right, and on the top here we have, this is our difference quotient. This is our y2 minus y1 over x2 minus x1, right? That's the slope of our secant line. That's this part. That's our average rate of change. That's our average rate of change. Once we run that limiting process on it and bring that h to 0, right? We're moving this point in, right? And we get closer and closer and closer till we finally arrive, if you will, at the slope of the tangent, right? The derivative, the slope of the tangent line. That then is our instantaneous rate of change, right? Instantaneous being the key word. So this is our average rate of change part. Once we run the limiting process on that, that'll get us that instantaneous rate of change, the slope of that tangent line. So instantaneous rate of change. A few examples would be in population growth rates, production rates, water flow rates, velocity, acceleration, all that kind of stuff. We're going to be able to work with some of as well. Now let me give you a little. Now, if you remember, like our distance is rate times time, right? In other words, our rate is distance over time. In other words, our average rate, our average velocity then would be the change in our distance over change in time, right? And I'm going to use change in position over change in time. S denoting position. So this is change position, in other words, change in distance. And this is change in time, right? That's our average velocity, our pre-calculus stuff. So our instantaneous would then be if we run the limiting process on that change in position over change in time. That would be the instantaneous. So if you have position, if you know position, the derivative on that would be your, the derivative of your position would then be your velocity. There's a relationship here, right? The change in position, like if this is in feet, over change in time, like in seconds, right? The velocity would be in feet per second if your position's just in feet. So there's a relationship between these, and then the derivative of that is your acceleration. Okay, so this is what you want to remember on that is the with that limiting process, we can get to the velocity, which is the derivative of the position. Okay, so position, which our units are usually like feet or meters or whatever. Velocity is just the derivative of position. It's the instantaneous rate of change of the position. Okay, the acceleration is the derivative of velocity. So it's the instantaneous rate of change of the velocity. In other words, the second derivative of the position. And velocity would be in like feet per second. And then your acceleration would be like feet per second squared. Okay. Now, velocity has direction. So like, for example, if your velocity is negative and you're going up or down, vertically or down towards the earth or whatever, if your velocity is negative, that means you're going towards the earth, right? Speed, on the other hand, has no direction. So speed is the absolute value of velocity. Even though your velocity might be, I'm going negative 100 miles per hour, falling towards the earth, your speed would be 100 miles per hour. I'm traveling 100 miles per hour. So again, speed is the absolute value of velocity. Speed does not have direction. Velocity has direction. Okay, we'll talk more about that. Now we don't get into jerk a whole lot, but just be aware that, or at all in this course, It's the derivative of acceleration, okay? So jerk is just a jolt, surge, or lurch. So a sudden change in acceleration. So that's the third derivative of position, or the second derivative of velocity, or the first derivative of acceleration. That's called a jerk. If you take a calculus-based physics course, you might get more into that, or go into some other STEM courses. All right, now the position of a body moving along coordinate line at time t, and shortly at time t when you're moving along just a horizontal axis, right? So let's say you start right here. If you have positive velocity, that means you're going, we'll say in this case, to the right. If you have negative velocity, that means that particle would be moving the opposite direction, to the left, okay? So let's do some analysis of that. For example, if you have a time with your position, so this is a position graph, okay? And notice it says here the derivative of position, which we know the derivative of position is velocity, right? So if your velocity is, oh, I'm sorry, my goodness, I said this wrong. If your velocity is positive, good grief, you're going away. I meant to say velocity, my apologies. You're going to the right here. If your velocity is negative, now you're going back towards the left there. Okay. All right, so back to our position graph. So notice if I was to look at, if I was just to take a point and look at the slope of the tangent, like it's positive. Wherever it's at, it's positive, right? So the derivative is positive. In other words, the velocity is positive. So this particle is going to the right. If you're having the particle on a horizontal axis, going to the right. If you're having the particle on a vertical axis, then it's moving up, because the velocity is positive, moving up. In other words, at 1 second, maybe it's only 10 feet away, right? After 1 second, it's 10 feet away from the origin. Or if you're going up, down, you know, if this is the ground, at 10 seconds, you're 10 feet high, okay? But after 3 seconds, now it's 30 feet away, right? Because the velocity is positive, it's still going to the right, or if it's going up, down, it's still going up, right? Whereas over here, this is a time with position as a position graph. Now your slope of the tangents are negative, so that thing's moving in a negative direction. It's going that way if it's going right or left. If it's up, down, that means it's moving downward, okay? Here's an example. You know, if you drive to a friend's house and back at 30 miles per hour, speedometer will show 30 on the way over. It's not going to show your velocity. It's not going to show negative 30 on the way back, even though the distance from the home is decreasing, right? The speedometer will show speed. It's just showing your speed, the absolute value of velocity. So speed measures rate of progress regardless of direction. Let's do some more analysis here with this particle moving right or left here. Okay, if it's moving right, meaning our velocity is positive. If it's moving left, it's negative, right? So let's look at this. We have a position graph. Here's our position. T time, horizontal axis, vertical axis, position here. So this is saying after 1 second, we're 2 centimeters away. All right, so we started here. Let's see, we started here. After 1 second, we're 2 centimeters away. Okay. At the second, so this whole time, notice it stayed. It's still 2 centimeters away. So what did the particle do? It just stayed there, it just stopped. So during this time period, what's the derivative there? Well, the derivative is the slope of the tangent line. So this is up 2 over 1. The velocity was 2, is going 2 centimeters per second to the right. And then it just stopped, right? What's our slope right here? Slope is 0, so it just stopped. Right? So the velocity, in other words, because that's the derivative of the position. The velocity's 0, so it stopped. And now what's the slope here? Now we went down 4, right 1. Slope here is -4. So now I'm going backwards for a set at 4 centimeters per second, right? Boom. 4 centimeters per second. And then the slope's 0, so then it just stops again for 2 seconds between the 3rd and the 5th second. Just stops. And then what does it do again? Keeps going that direction at a rate of 2 centimeters per second, right? Slope -2. And that's all the information we have there. So, A, when is P moving to the left? Well, we know it's moving left when velocity, which is the derivative of the position, is negative. Well, when does that happen? Right here, right? So t being less than 3 greater than 2, and right here, or t being less than 6 greater than 5. Okay, when is it moving to the right? When the velocity, which is again the slope of the tangent line, so the derivative of position, is positive. So that'd be right here, between 0 and 1. When is it standing still? That's when our slope is 0, so between 1 and 2. Or right here as well, between 3 and 5. That's when it's standing still, right? Now, part B, graph the particle's velocity and speed. I better clean this up a little bit. Alright, so let's do t and v of t, which is the same as s prime of t. Now let's do it for t being between 0 and 1. So when t is between 0 and 1, what's the slope? Up 2 and right 1. 2 over 1 is 2. Now when t is between 1 and 2, now our slope is 0. When t is between 2 and 3, now we're going down 4, right 1, so -4 over 1 is -4. When t is between 3 and 5, slope is 0. When t is between 5 and 6, looks like we're down to right 1, -2. And so we just graph it like that. T, v of t, when t is between 0 and 1, it's 2. Between 0 and 1 is 2. When t is between 1 and 2, it's 0. When t is between 2 and 3, it's -4. When t is between 3 and 5, it's 0. And when t is between 5 and 6, it's -2. Okay? So that's the velocity. Now remember speed is the absolute value of velocity. Well, that's not, absolute value of 2 is 2. Absolute value 0, 0. Absolute value negative 4, though, is 4. Absolute value negative 2 is 2. So when I do speed, these are the same, but this negative 4 will go up here to 4. Oops, that's supposed to be there at 4. This negative 2, absolute value negative 2 is 2, right? Because the speed is not negative 2, the speed is just 2 on that. So that's the only thing that changes. There's a graph of both of those, velocity and the speed there. Let's keep going here. Given the position of a body moving in a coordinate line with s in meters, t in seconds, find the body's displacement and average velocity. Average velocity, so that's just the slope, okay? Average velocity, pre-calculus, for the given time interval. So first of all, let's do the displacement. That's saying if s of t is 6t minus t squared over this interval from 0 to 6, where is it at the 6th second as compared to the 0th second when it began? So 6 times 6 minus 6 squared. So 6 seconds, it's at 0 meters. At 0 seconds, it looks like it's at 0 meters. So the displacement is the difference between the two. So 0 meters. Now, like sometimes maybe let's say it was s of 6 was 10. Then it'd be 10 minus 0, right? The total displacement was 10 meters. So that's why you're finding the difference there. Or, you know, the displacement on an interval from 1 to 6. And you go s of 6 minus s of 0. So again, it's just the change. It's just the change in your positions there over whatever interval they're asking for. Now, for the average velocity, the average velocity on that, average velocity. Remember, average, this is just a slope, right? So we're going y2 minus y1 over x2 minus x1. So that's 0, that's 0. So 0 over 6, average velocity, and this is meters per second, right? Because this one's in meters, that one's in seconds. So 0 meters per second, kind of boring on that one. B, find the body's speed and acceleration at the endpoints of the interval. Let me erase this thing. All right, you know what, to find speed, I know speed is the absolute value of velocity. So what I'm going to do first is let's find the velocity, which is the derivative of position. Now here's our position, right? So we know derivative of 6t is just 6. Derivative negative t squared, the negative stays there in front, the negative 1 in front, and then I take the derivative t squared, 2t to the 1. So our velocity is 6 minus 2t. Okay. Now it wants the speed at the endpoints. And then we'll do the acceleration. Okay. So s of 0, speed at t being 0, is the absolute value of the velocity at 0. So the absolute value of 6 minus 2 times 0. Well, 6 minus 0 is 6. So we got 6. This is meters per second. That's our speed. The other endpoint would be the speed at t being 6. So we got the absolute value of the velocity at 6 seconds. So 6 minus 2 times 6. So the velocity, 6 minus 12 is negative 6. The velocity is negative 6 meters per second, right? This thing's going down or to the left, again, depending on this moving body. But the absolute value of -6 is 6. So the speed, again, has no direction. So 6 meters per second. Now the acceleration. Well, we know the velocity is -2t plus 6. So the acceleration is the derivative of that. So -2. And this is feet per second squared, right? It goes feet for position. Oh, I'm sorry, meters in this case. This is meters. My apologies. Meters per second squared. Meters for position, meters per second for velocity, meters per second squared for acceleration. Okay. But we want the acceleration at the endpoints. Well, there's no zero to plug in. There's no t to plug in for zero. Zero to plug in for t. So it's just -2 meters per second squared. Acceleration is 6. -2. Again, there's no t to plug into. Meters per second squared on that. Part C. When, if ever, does the interval when, if ever, during the interval, does the body change direction? Remember, velocity gives us direction. Velocity gives us direction. So the question is, we have this velocity, -2t plus 6. In fact, let me look at the graph for a minute. 3, 4, 5, 6. If I was to graph this, it kind of looks like that kind of thing, right? This whole time, this velocity, this positive, right? And then down here, your y's are all negative. So the velocity is all positive up here. Velocity is all negative down here. That's the point at which it changes direction. It's the zero. I just want to find the zero, right? Because I know it goes from positive to negative, so it does change direction. Now, if the graph had gone and hit and then gone back up, then it never changed direction. And the velocity stopped, but it never changed direction. It has to go from positive to negative, or vice versa, negative to positive. And this one does. It goes from positives to negatives. So you solve this, subtract 6, divide by -2, and so on. You get it at 3 seconds. All right, so it changes direction at 3 seconds on this thing. And here's just the graphs of the 6t minus t squared, the position. You can see in red there. And notice the derivative right here is 0 at t equals 3. There's the derivative in blue. What's its derivative? T, the value 0, right? And then we take the derivative of -2t, and it's -2, right? This slope of this tangent this whole time is -2 right there, right? All right, what about a velocity graph? Okay, so we've got time still, but now we've got velocity. So notice in blue here, this is when it's always, we're positive. Velocity is positive, right? So this thing's moving forward. Okay, the particle is moving forward. If it's on a horizontal axis, it's moving forward during that time from 0 to 3. It's moving for 0 to 3 seconds. And then it stops, velocity is 0, and then that thing goes backwards between 3 and 5 seconds, right? Between 3 and 5 seconds. And then it stops between the 5th and 6th seconds. The velocity is 0 that whole time. And then it goes back to the right again. Speeds up. So I'm not very good at doing this, but I'm also going to show you, hey, this velocity is speeding up, right? It's going like at a half second, it's whatever velocity, maybe 5 feet per second. But at 1, now it's at 10 feet per second, right? It's speeding up. And then it's like the same velocity, like it's going 10 feet per second this whole time between the first and second, even though it's still going to the right, and then it slows down. So let me do my best here to kind of do that. So it's speeding up, and then it holds it, and then, but it's still going to the right. And then it stops at that 3rd second right there, velocity 0 there. And then, gosh, I can't do this very well, but I'm trying here. And then now it's going to the left, right? Oh my goodness gracious, why does that thing keep moving? Now it's going to the left. And it's going, so it goes between the 3rd and 5th second. And it's speeding up even though it's going to the left. right? This rate of change there, slope of the tangent is pretty steep there. So go, and then it kind of, and then slope of the tangent, rate of change 0 right there. Still going to the left, and it kind of peters off. It's at a standstill between the 5th and 6th seconds, and then it speeds up again, going to the right. Not constant, speeding up. I really struggle with that, but anyways, you can kind of see what I'm trying to get at there, hopefully. There's a good description also in the other slides. All right, free fall from the Tower of Pisa. So it had Galileo dropped a cannonball from the Tower of Pisa 179 feet above the ground. The ball's height, so we have a position here, above the ground t seconds into the fall would have been, so here's our position, negative 16t squared plus 179. Part A. What would have been the ball's velocity? Well, we know the velocity is the derivative of the position, negative 32t, derivative of 179 is 0. If this is feet, this would be in feet per second. What's the speed? Speed is just absolute value of that velocity. So absolute value, negative 32t, right? It's 32t. Acceleration, derivative velocity, second derivative position. So I take the derivative of negative 32t, negative 32. And this is feet per second squared. There's our acceleration. Part B, about how long would it have taken the ball to hit the ground? Well, it hits the ground when your position is 0, right? If your position is 10 feet, you're 10 feet high in the air. If your position is 0, you hit the ground. So when does the position 0? When does it hit the ground? So we got square root plus minus, but of course it's positive. Time is positive here, right? That's your time, which is, let me see what that is. 3.3 seconds. So about 3.3 seconds it hits the ground. Okay. Part C, what would have been the ball's velocity at the moment of impact? So right when it hits the ground, what's the velocity at this 3.3 seconds? So let me plug it into my velocity, negative 32t. And it ends up being negative, it's going down, right? Dropping at 107 feet per second when it smacks the ground. Right, if you drop this cannonball from the Tower of Pisa. All right, some graphs here. Let's see if we can figure out whose position, whose velocity, and who is acceleration. Now, what I like to do is, especially if it looks like a bunch of polynomials, I want to think to myself, well, the derivative, when I'm using the power rule, is going to, when I take the derivative, it's going to decrease the power by 1, right? So like that red one there, C, it looks like it's a cubic function, right? If the red one is a cubic function, my gosh, what's wrong with this thing? If it's a cubic function, the red one, C, then when I take its derivative, it's quadratic. When I take its derivative, it's a linear. You see what I'm saying? So C would have to be the position, the cubic. The quadratic, A, would be the velocity, and then B would be the linear position because they go down by degree as you take the derivative. All right, so CAB. Now, another way to think about this, let me erase this real fast. Oops. is when I'm looking at this slope of the tangent right there. That slope is 0. So its derivative should have a slope of 0, right? And then now look at that quadratic. That's when its tangent line, the slope of its tangent is 0. So its derivative is the yellow one. So C's derivative is right there. C's derivative is A. And then A's derivative, that x value, is B. So again, CAB, position, velocity, acceleration. Okay. Thanks so much for listening. We will see you guys next time.